This is the very last one. So this is part 3, and this is just finishing this example. And if you are waiting to watch this for when Mikolaitis is going to start teaching, for after that, you're going to be in trouble. Oh my goodness, so now my daughter arrived, and my cat. Okay, so I have some help. If you're watching this after Mikolaitis started entropy, you are in serious trouble. Like, I am telling you guys, I am doing this very gradually and trying to help you guys out, but you need to be responsible. If Mikolaitis starts on Monday talking about the second law in entropy, and you guys need more time to watch our videos, my videos, you can ask him. Pretty sure he's gonna say no though, because he has a plan and he's to be responsible, which is ironic. Well, not ironic, but if you're watching this, then you are being responsible. So this message is not for you, but tell your friends, tell the others on GroupMe or wherever you guys are. Watch these videos; they're not that bad. I'm just going over the notes, and if someone doesn't want to watch them, just go over the notes, okay? Alright, mi amor, voy a hacer esto, ¿sabes? Pero no tiene que ir, te puede quedar, pero it might be boring for you. I love you. Alright, so on the previous video, I started this problem, okay, which is the Brayton cycle. Now, we said that we needed to find a bunch of values. We started with the first one. The first one was T2. And then we said that for T2, we don't have, for example, U or H or another property that we can use to go to the table and find H2, and find T2. So we're going to use the first law. Just some fun. Ow! If you've watched up to this point, you deserve to watch this beautiful ragdoll cat. I'm sorry, Roger. Alright, that's good enough. Okay. Alright, so and then we decided to use the first law for the compressor. And we said that the specific word of the compressor is H2 minus H1. We can find H1 at the temperature. So we can, because we have T1, and then we can solve for H2. And then if we got it with H2 to the tables, everything else in that row, you're gonna need this for later, corresponds to that state. You're gonna use that row for other stuff, for PR, VR, and S naught, which is S with a little 0 at the top. So we have to interpolate to find T2 because that value of H2 is not there. And that's what I did over here, right? You can see it on the notes. I did the interpolation between 530 and 540. It's closer to 540, 537.15 Kelvin. That will be T2. And it makes sense that it's increasing because we have energy going in. And, oh my goodness. We have energy going in, and it's increasing the energy. So it's going to be increasing the total energy of my ideal gas. And then, as we know, specific internal energy or specific enthalpy of the ideal gas, it varies with temperature. Varies with temperature only. So temperature, we expect it to increase. Now, to find T3, if we had Qn, you should be getting used to this by now. If we had Qn, we could just use Qn equal to H3 minus H2. And we can solve for H3, do the same thing. But we don't have that. So then we have to figure out what do we have, to find that value of T3. Now, this one is a tricky one because, it looks easy once I solve for it, but figuring out what to use is the tricky one. So I have that for constant pressure in an ideal gas, all right? I also have that V over T is constant, but that's not helpful. So what I'm using there, what you're seeing there is m dot. M dot at 2 is equal to m dot at 3, okay? M dot for steady state and one-dimensional flow, we decided that is AV divided by specific volume, and for an ideal gas, that is equal to PAV divided by RT, where that V is velocity, okay? So when, pressure is constant, it cancels out, which is what you see there. And then R is just the gas constant, and this is air, which is 0.287 units, so it cancels out as well. And we end up with AV, volumetric flow rate, it's area and velocity divided by T, constant from 2 to 3, okay? This PAV divided by RT at 1 is equal to the value of 2, equal to the value of 3, equal to the value of 4, because this is m dot, okay? Now here we can solve for T3 using this, and this problem is one of those creative problems I come up with. Actually, I'm making your open system problem for your exam, or problems. So please try to understand this, okay? Yeah, anyway, so then we can solve for T3, and it ends up being 1300 Kelvin, that beautiful number without decimal places, and well, I mean, it has decimal places 0, but it's not like 1298.75 because I came out with a problem with the numbers such that you would get that value of T3. And here we see another way to find temperature. The first one was using conservation of energy. The second one was using the fact that m dot is constant because we have steady state, okay? The next thing that it's asking for is a specific work out of the turbine, and that will be H3 minus H4. If you look at your handout, the supplemental thing for open systems, the power is m dot H3 minus H4. Now we need to find H3 and H4. For this, we need T3 and T4, and that's why I found T3. Right? I don't have to say it. I don't have to say find T3, and then you have to go ahead and do the whole procedure and find it anyway. So I said it on the exam because this is an exam problem. Just so I would guide them, okay? T4 is given as 770. T3 we just found. I'm sorry. T3 we just found, and then we find the values of H from table A17. Table A17. Yeah, I'm showing you my soft arm. It'll get better later. I'm just old. Actually, that won't get better with age. But I will start working out or something. T3 we solved for. T4 was given. We find H from A17, so that one is better. It's a little easier. We don't have to think too much, like what do I have to use, like finding T2 and T3. That's the part that's like, what do I use? So this is good practice because you're gonna have to think a little bit on the problem that I give you, even if it's take home or something like that, like Nikolai is gonna do. Someone asked me about that, like is this acceptable to everyone to take home? Well, I mean, they're basically all take home now because you're home and we can't see you, and we're not going to use ProctorU, so we're just going to trust you. And since you're going to have on your record that you passed thermal when you go to work, if someone sees that, they'll expect you to know something. So do yourself a favor and try to understand, okay? Even if you don't understand 100%, try to understand like 75 or 80%, like I sometimes ask you guys in class, okay? Anyway, now it's asking for Q in and Q out. Q in, H3 minus H2. High minus low. Q out, which one is the high one there? 4 or 1? What do you think? There's energy coming out, so that means that the high one is 4, okay? So it'll be H4 minus H1. So now it's just a matter of finding all the values of H, and we have all the temperature values, so we can find them. We already found H1. We solved for H2. We found H3 and H4 for the work of the turbine, so we can solve for Q in and Q out, okay? That's good. Now, the problem first part. Part B is using constant specific heat at 300 Kelvin. CP at 300 Kelvin is 1.005 units, which is what it says there. CV is 0.718 units, which doesn't say there because we don't use it here. For ideal gases, and this is on the handouts that you have and that I gave you for the future, for ideal gases and constant specific heat, delta U is CV delta T, delta H is CP delta T. Now, for the compressor, let's see. Before I talk about that, here it told you to find it at 300 Kelvin. So the answer at the top for the question, why are they so different, even before we solve for it, they are very different. First, because part B is an approximation. And second, because we're solving this at 300 Kelvin and we see that the temperature is increasing from 300 to 537 to 1300 and then decreasing to 770. If we found an average value for temperature for each process and then found CP at the average value and substituted for that for conservation of energy, it might help. But we're not doing that. We're doing it at 300 Kelvin. So now we're going to do the same procedure, all right? To find a T2, we're going to use conservation of energy for the compressor. It's H2 minus H1 like you see on part A, but that's equal to CP, T2 minus T1. So now we don't have to interpolate because now that work of the compressor, which is given, this part over here, okay, that work of the compressor is equal to an equation where you have two known values and one unknown. So you solve for T2. Then from 2 to 3, same procedure. So you already did the hard part, which was figuring out what to use to find T3. So I used the same thing, m dot 2 equal to m dot 3. And I solve for T3. And up till there, not that different. Now, let's see. So the next part is finding WT, Q in, and Q out. And all of this delta H equation, all these delta H equations we change to CP delta T corresponding. So when we have H3 minus H4, CP T3 minus T4. And then all the values of T, we have them, so we substitute in there. And then you see that, for example, Q in, which was 854, okay? Switch H3 minus H2, now is 771. That's pretty different, okay? And this, especially that one, because T2 and T3 are the highest temperature values, and we're still using CP at 300, so obviously it's going to give us just pretty far off. Now you'll learn later when you see the full air standard cycles why we use those approximations. That's it. That's my parts. I'll apologize again for taking this leave. If you want to see my scars or something, I'll be happy to show them to you. This surgery was more major than I had anticipated, and I was still planning on coming back. I recorded a few lectures for you, but the recovery, which was right after spring break, did not go as planned because I was stressing out. I thought I had to change your class to online, and my daughter was home, and she's great, but I was stressing out about the logistics of this unknown situation and just like out of the blue, and I started having issues, and recovery did not start well, and that's what ruined everything afterwards. So I apologize, but I'm not just gonna leave you. Mikolaitis is great. He's very excited to be with you guys now, and he's very smart. You guys can learn so much from him, especially now that you don't have that much pressure because you come in with a high grade, and I'm around. Like I said, I opened that Facebook group. You can ask me questions, and I'm sorry I didn't get to know you guys better. What I did see, I really loved, and it doesn't matter, you guys didn't do well in the second exam. It's just, we all have, our moments. You guys were great, just very energetic in the class, and you made me laugh a lot, and I really miss seeing you guys. I do. I'm not gonna cry. I will be around, like I said, and I wish you the best this semester. That is so strange. And I hope you stay healthy and your family does too. And I hope I see you around campus later. Okay? So, good luck. And why can't I end with like a beautiful phrase? Just take care of yourselves. Okay. I'll see you guys later.